Hi, so excited to see you. I don't see you. You see me, but I don't see you. Okay, so for today's lesson, you need your textbook, you need your notebook, and you need your pink sheet, your formula sheet. Specifically, you need to go find the 2 pages that say negative z-score and positive z-score. Now, I know your sheet's stapled together, mine folds out lovely, but find those 2, you kind of need them side by side, okay? So we're starting chapter 6, and I am going to, like I did before, I'm going to kind of shorten things up and make this just as what you need, not a whole lot of extra. But this actually gets to be kind of not only a really, really important chapter, it's a little bit longer and has some really important stuff in it. So today we're going to start with 6.1 and 6.2. And like I said, textbook, calculator, and your z-score sheet. Now, first of all, you should have already watched video number 7 that I sent you. And for those of you who were also in calculus class with me, I don't know if you noticed, you probably didn't, but at one point they were talking about the fact that they were graphing and studying the rates of how many birds per net per day were being caught. So remember, in calculus, per day, per net, that's a rate. And everything we did in calculus had to do with rates. And so this class is usually in college a class that you take after calculus, because as you're going to see today, we're kind of doing some stuff that really could have been done with calculus. So lucky for you, you are in elementary statistics and it's not calculus based. Okay, so before we went on apocalypse teaching at home, we looked a little bit at the normal curve. And the example that we did back then was we talked about IQ of the whole population. And I told you at that point, and this was true then, it's still true now, that the mean for population for IQ, the mean or average IQ of all people is 100. And the standard deviation, sigma, for the population is 15. So we talked about what that means. Now, I'm going to put a bunch of things together that we've talked about already. We talked about the range rule of thumb. So the range rule of thumb says that usual values fall between 2 standard deviations from the mean. So if I were to ask you, is it unusual for a person to have an IQ of, let me make that up, 138. So we're wondering about the one particular IQ of 138, and using our range rule of thumb, that would mean they'd have to be more than 2 standard deviations above or below. Okay, so we did 100 as our mean, and then we did our 2 standard deviations. So 1 standard deviation above would be 115, and 1 below would be 85, and 2 standard deviations, so 30 above, would be 130, and 30 below would be 70. So if I asked you with our chapter 5 stuff whether or not it's unusual for someone to have an IQ of 138, well, they would have to be more than or less than 2 standard deviations. So is a person with an IQ of 138 unusual? Yes, because it's more than the 2 standard deviations from the mean. Now, so that's range rule of thumb. Okay. We also talked about the empirical rule back then. I'll probably spend that long, who cares? In the empirical rule, we also looked at this, and we said that was the 68, 95, 99.7 rule. So, 1 standard deviation from the mean, below or above, 68% of the population would be in. 95% of the population would be within 2 standard deviations of the mean. 2 standard deviations of the mean, range rule of thumb, usual. So that means 95% of the population, that's why they're considered usual. And then 3 standard deviations from the mean, we're really getting into the unusual, the really high and the really low. Okay, so that was the first thing. Now, we also talked about another kind of distribution, and that was uniform distribution. And at this point, pause the video if you need to grab your textbooks and go to page 246. We're going to do a quick example. And the reason we're looking at the uniform distribution example is because this is really going to help us understand the concept of what we're going to be doing with our normal. So on that page, you have the example about subway waiting time. It says, given the uniform distribution illustrated in the figure below, find the probability that randomly selected passenger has a waiting time greater than 2 minutes. Okay, so you've got the graph in your book, but I want you to throw it in your notes as well. So we're talking about people waiting for a subway, and they can wait for 1 minute, 2 minutes, 3 minutes, 4 minutes, or 5 minutes. Now, we're going someplace really, really important with this, so do pay attention even though it doesn't seem that important. And our y-axis is actually our probability. Okay, in the example there, they have put point 2 and drawn this nice, straight, uniform curve for point 2. The question is, what is the probability of waiting more than 2? Now, we can only wait 2 to 5. So that means 2 to 5. And here comes that thing looking like calculus again. So this looks like our rectangle approximation method where we first started learning in calculus about how to find the area under the curve. Okay, now, a probability distribution can be graphed, or we can do our table. We've been doing these tables. So let me just make these come together. In this particular distribution, it's uniform. Our x's can be 1, 2, 3, 4, or 5. I'm going to need numerical x value. Our probabilities then are constant. Each one of these has the same probability of 0.2. Remember, for it to be a probability distribution, the sum of the probabilities has to equal 1. 2, 4, 6, 8, 10. Yep, equals 1. So this is a probability distribution that happens to be uniform. This is also a probability distribution that is not uniform. And we're going to be taking this concept and going into all stuff normal after this. Okay, so what is the probability of waiting more than 2? Well, that doesn't mean to wait 2, it means all of the ones more than 2. So waiting 3, 4, or 5. 3 or 4 or 5, and we already know that or is plus. We're simply adding these together. 2.2, 0.2, and 0.2. Okay? We get 0.6. So the probability of waiting more than 2 minutes is 0.6. Okay. How does that work if we're looking at it graphically? Area under a distribution curve is probability. So the probability can be found if I can calculate the area under this curve. How wide is this? Well, it's 3. 1, 2, 3. How high? Area is length times width. It has a width of 0.2. It has a length of 3. And we get the same 0.6. Okay? So a graph of a probability distribution, a table of a probability distribution, it's all the same. The big takeaway you need, and this needs to go in your notebooks and write this down, this is huge, this is now like the important thing. The area gives you your probability. So I'm going to write this here and keep this here. The area under your probability distribution curve is actually the probability. So when I'm going to be asking you in the near future, what is the probability that, blah, 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 you're going to be looking for the area under the curve. Okay. So now, let's take this to the next notch. We did the IQ example, and our mean was 100. But now what we're going to be doing is actually using the standard normal. You guys have been taking tests your whole lives. You're seniors. You all took the SAT. The SAT is a standardized test. What the SAT does is it doesn't come out and say, oh, this kid Joey over here has a 98% on the test. No. You have that maximum score, whatever it is nowadays, that maximum SAT score, but they don't tell you you got a 98. They're not actually rating you alone. They're rating you against the population of everybody who's taken the SAT. They've standardized your score for the sole purpose of comparing you to the other people trying to get into college. Okay. In the standard normal, we've standardized it by making the mean and the standard deviation the same for all populations. In the standard normal, your mean is 0 and your standard deviation is 1. Okay. So, in your notebooks, we need a normal curve. By the way, you're going to be drawing these for every single problem you do from now on. This is going to be important. So now what we're saying is the guy right in the middle of the population is at 0. That's really no different than what we do when we graph, right? We have our coordinate system here. Here's 0, 0. We like starting at 0. Starting at 0 makes life make a little bit more sense. People who are above average are over here in positive values. People that are below average are over here in negative values. So now, if you're above average, you're 1 or 2 or 3 or more standard deviations above the mean. And if you're below average, you're -1, -2, or -3. The probability of where you fall is going to be where the area under this curve falls. Okay, so let me try to start explaining this. Take out your negative z-score and positive z-score chart. Way back in chapter 3, I think it was, we looked just for a quick minute at z-scores, and I told you way back then we're going to come back to this a lot. So if you look in your chapter 6 formula sheet, you will find the formula for the z-score. This is the thing you need, and this is the thing you need for pretty much everything moving forward, okay? So our z-score formula is, we're going to take any individual x value. Like a minute ago I gave you that example with an IQ of 138. So we'd say x is 138. Then we're going to subtract from that the mean. And then we're going to divide by the standard deviation. So I'm going to go back and think about that for a second. We are wondering exactly where an IQ of 138 fell. We'll come back to that. Now this is our population Z formula. If I'm doing my sample Z formula. It's the same, but our notation is different. We take our x value, we're going to subtract it from the mean, which we call x bar, if we're doing a sample, and we're going to divide by our standard deviation, which we call S, if we're doing a sample. Okay. Now, before I get into all the rest of this stuff, let me just talk about how to use this chart. I'm going to do a second video on more of these calculations. Okay. So, let's say we come and find out that we have a z-score. I'm not going to calculate one right now. Let's say we have a z-score of negative 1.3. Now, the really, really, really important thing to know, besides this, here's one of them. That's important. The second important thing to know is that your z-score is your standard deviation. That's what a z-score is. It is sigma. It's just a way more exact sigma. So instead of talking about being 1, 2, or 3 standard deviations from the mean, we're going to talk about things like, what if I'm 1.3 standard deviations below the mean? It's negative. Where do I fall? Okay. So we know in general, if we want to use some common sense, that negative 1.3 is lower than negative 1. So it's, somewhere around here. It's below negative 1. Okay. Probabilities are the area under the curve. So what we're saying is, this z-score chart, which I'm going to show you in a minute, gives us the area under this curve from the far left up to the z-score. Up to the z-score. Okay. So I'm wondering what the probability of being negative 1.3 standard deviations below the mean. So let's go to our chart. Because our z-score is negative, you're going to want to go to the negative z-score value. Okay. Down this column is all of the z-scores rounded to 1 decimal place. So we are looking for negative 1.3. Okay. Negative 1.3 is right there. Okay. Negative 1.3, the area, so this whole body of the chart here is actually giving you the area from the left to the z-score. That's why it looks like this. So that value is, my glasses are not on. 0.1151. 0.1151. Okay. Negative 1.3 is right above that. 0.0968. 0.0968. Okay, what the heck does that mean? Okay, that means that this blue area has an area of 0.0968. If I were to shade in the whole bell curve, normal curve, it would equal 1. Because all the probabilities in a distribution always add to 1. And the area under this curve is the probability. So all of the probabilities, all of the shading, all of the area will be 1. So the probability of falling at a z-score, a sigma, a standard deviation, of 1.3 below the mean is 0.0968. In terms of population, I know we don't write things this way, but what this means is 9.68% of the population, let's just say this was your SAT score, 9.68% of people would fall below this standard deviation of the mean. Okay. Let's do another one. What if instead of negative 1.3, I wanted to know the population or the probability of a z-score of negative, I'll start with 1.3 again. 1.38. Okay, so now let's get into reading this chart. If you look across the top of the chart, there are decimal values, 0.00, 0.01, 0.02, blah, blah, blah. This is because all z-scores need to be rounded to 2 decimal places. And so if I am going to look for the area at a z-score of negative 1.38, I am going to find the negative 1.3 down here, and then I'm going to add that 0.08 by coming across the top and finding the 0.08. So I'm looking for the 0.08, there it is, and I want to see where that's going to meet the negative 1.3. Negative 1.3 plus 0.8 meets at 0.838. 0.80, 0.0838. So 0.0838. So that means if I add a little bit more, so I'm actually moving a little bit left, I'm moving closer to negative 2. That means this line moves down a skosh. I have less area. Yeah, I do. I got 0.0838 instead of 0.0968. This is a worse z-score. This is further closer to the negative 2. Or 8.38% of the population falls in here. Now, let's do another one because I want to point out something. So that z-score calculation always starts collecting area from the left. Okay. This will be the last example I do in this video, and then I'm going to make another one. Do some real examples out of the book. So, there's my mean. Let's say I now have a z-score of 1, here's 2. Let's do a z of 2.05. Now, this means I now have the area starting at the left and going up to slightly over 2 standard deviations. So now that's a positive value. So I'm going to go to my positive z-score chart. I am looking for a value of 2.0 and then 0.5 more. So I'm looking for 2.0. Oh, there's 2.0. But I want 2.05. So I have to add 0.5. So I'm looking for where that 0.5 column is going to meet that 0.20 column. And it's right there, 0.9798. 0.9798. Okay, that means this area is 0.9798. But what if I asked you, what is the probability of a z-score